Question 12 gives us a bit more practice drawing structures based on the names, but what it's mainly about is this idea of classifying alcohols as primary, secondary or tertiary. Hopefully you're going to find that easy, because it's basically doing exactly the same thing as you've already learnt to do with carbocations. So you find the carbon that has the OH on it, and you just count, looking at its other bonds, how many of these are carbons. If you've just got one other carbon and say 2 hydrogens, or a hydrogen and a chlorine, whatever it might be, that's a primary alcohol because there's just one other carbon attached. If there are 2 other carbons, but this was a hydrogen or whatever, that would be a secondary alcohol. And if there are 3 other carbons, that's a tertiary alcohol. So that's a very familiar idea, because as I say, it's the same as you've already learnt to do with carbocations. And again, we're not doing this just for the hell of it. It matters because when we get onto oxidation reactions, which is where we're going in the next few questions, these things behave differently. Primary ones behave differently from secondary ones, which behave differently from tertiary ones in these important oxidation reactions. So that's why it's important to be good at doing this. Okay, so butan 1-ol. But means a chain of 4, and means it's saturated. So no carbon-carbon double bonds. And carbon 1, in other words at the end of the chain, is the ol, so carbon 1 has the OH. So that's butan 1-ol. And you can see that the carbon that has the OH is that one, and it has only one other carbon attached, so that one is primary. 2-methylbutan 1-ol. So again, there's our butan 1-ol. So if that's carbon 1, this is carbon 2, and so 2-methyl just means it has a methyl group attached there. So that's our structure. And again, you can see the fact that we've put that methyl group there makes no difference, because the carbon that has the OH still only has one other carbon attached, and therefore again that's a primary alcohol. 3-methylpentan 2-ol. So let's try that. Pentan means you have an unsaturated chain of 5. Pentan 2-ol means that carbon 2, the second one along in the chain, has the OH group on board. Again, notice how careful I'm being to make sure that the bond connects to the oxygen, not to the hydrogen, when you're drawing these structures. You've got to always pay attention to that. So that would be pentan 2-ol, but we've got 3-methyl pentan 2-ol, so this is carbon 3, which has a methyl group, so that's there. So now you can see this one isn't primary, because there's the carbon with the OH, and it has 2 other carbons attached, so that one is a secondary alcohol. 2-methylpropan 2-ol. Propan is a chain of 3, saturated chain, and you can see that carbon 2 has both a methyl group and the OH group, so it's going to look like this. And that is a tertiary alcohol, because the carbon with the OH has 3 other carbons attached. So 2-methylpropan 2-ol is a tertiary alcohol. Cyclohexanol means you have a ring of 6, that's the cyclohexane bit, and one of those carbons has the OH on, so that's cyclohexanol. And you can see that's secondary, because there's the carbon with the OH and it has 2 other carbons attached. So the fact that it's in a ring doesn't make any difference, that's a secondary alcohol. So then these last 3 are obviously all isomers, where we're just moving the OH group around. So let's just get the basic structure sorted out first. So we've got triethyl octan 1-ol. So octan is a chain of 8, 1, 2, 3, 4, 5, 6, 7, 8. And no carbon-carbon double bonds, that's what the an means. And then 3, 4 and 6 have ethyl groups, which are 2 carbon branches. So if that's carbon 1, 2, 3 has an ethyl group, 4 has an ethyl group, that's 5, and 6 is here, which also has an ethyl group. So that's 3,4,6 triethyl octane. But we want 3,4,6 triethyl octan 1-ol. So here's carbon 1, and ol means it has the OH on board. which draw like that, so the bond's connected to the oxygen. So you can see that despite all these branches and the complexity down there, this is just a primary alcohol, because the carbon with the OH has just one other carbon attached, so that one is primary. So we can draw the same framework for the other ones, because they're all based on this 3,4,6 triethyl octane. So we've got that, and then we've got it again here. So here and here and here. Okay, so this one, 3,4,6 triethyl octan 4-ol. So this time the OH is on carbon 4. So that's 1, 2, 3, 4. So there is the OH. Okay, and you can see this time it's a tertiary alcohol, because the carbon with the OH has 1, 2, 3 other carbons attached. So that one is a tertiary alcohol. And finally 3,4,6 triethyl octan 5-ol. So 1, 2, 3, 4, 5 is this carbon. So that has the OH, and that one you can see is secondary, because the carbon has 2 other carbons attached. So that's a secondary alcohol. Question 13 then introduces these new functional groups, which are the kind of things that are created when alcohols are oxidized, which is why we're bringing them in now. So this one has C double bond O at the end of a chain. So C double bond O is called a carbonyl group. Okay, and that's really common in all sorts of organic compounds. But the point about carbonyl groups is that they behave very differently depending on what's on either side of them. So when we're describing what functional groups a compound contains and consequently naming it and so on, we don't directly just call that a carbonyl group. We have to say, well, what kind of carbonyl group is it, depending on what's around it. So you need to get used to that word so you know what people are talking about when they talk about C double bond O. But here we've got 2 specific kinds of environment. So when you have C double bond O and there's a carbon on one side but a hydrogen on the other, which is where you have a carbonyl at the end of a chain, like in this one, that's called an aldehyde. Okay, so you need to learn to recognise those, that it's a carbon, then C double bond O and just an H. So it comes at the end of a chain. And that's called an aldehyde, and they are named by sticking al on the end of the name. On the other hand, if you have a carbonyl group with carbons on both sides of it, that's called a ketone. In lots of ways, aldehydes and ketones behave similarly. We'll study their chemistry next year. In lots of ways, they're sort of, 2 sides of the same coin, but they have important differences as well, particularly in their redox chemistry, and that's why they get classified as different types of compound. And the way you name ketones is using the ending "one". Okay, so those are the basic ideas that we need to use to name these compounds. So this one, as we say, is an aldehyde, because the C double bond O is at the end of the chain. There would just be a hydrogen there, because that carbon at the moment obviously only has 3 bonds. So how do we name it? Well, there are 1, 2, 3, 4, 5 carbons, so it's pent. It's a saturated chain. Remember, C double bond O doesn't make it unsaturated. It has to be C double bond C. So that's still saturated, so it's pentan. And then we just put al on the end. We don't have to call it pentan 1-al, because by definition, if it's an aldehyde, the carbonyl is at the end of the chain, so it's automatically carbon 1 when you do that. So that's just called pentanal. Now this one, you can see, on the other hand, is like this, that the C double bond O, the carbonyl group, has carbons on both sides of it. So that fits this model, so this one is called a ketone. And to name it, well, again, it's saturated chain of 5, so it's pentan, but because it's a ketone, it's one. Now I've left the gap there because this time we do need a number to say where the carbonyl group is, because you can see that if you had that saturated chain of 5 and put the carbonyl there, that would still be a ketone, because you've got carbonyl with carbons on both sides, but it's a different compound. So the way you distinguish them is the usual way. You just number the carbons in the chain. So this would be 1, 2, 3 is where the ketone group is. So it's pentan 3-one. And this one would be pentan 2-one. Okay, so that's that one. Now this one, again we've got a chain of 5, but this time it's got an alkene group in it, a double bond, so that's going to make the name slightly more complicated. So it's not pentan this time, it's pent something ene, and I'll leave something to put the number in to say where the alkene group is, and then something one. Okay, because it's got the ketone group there, C double bond O with carbon on both sides, so that's where the one comes from, but it's also got an alkene group, so it's got the ene in there as well. So how are we going to number that? Well, this is our ending, one again, so that gets to have the lowest number. When you've got to decide on which end to start numbering from, you look first at the group which gives the ending, if there is one, and you make sure that gets the lowest number possible. So obviously that means you're going to want to number from this end, so it goes like this. So that means the ketone group comes at carbon 2, so it's 2-one, and the alkene group starts at carbon 3, so it's between 3 and 4, but remember you put the lower number down, so it's pent 3-ene 2-one, that compound. One other detail you could add to that, or should add to that really, is to notice that that has EZ isomers, right? Because the alkene group has 2 different groups at each end. So this carbon has this group here and a hydrogen, so 2 different groups. This one has a methyl group and a hydrogen. So we should apply the EZ rules, and you can see the priority groups are going to be this one and this one, so they're on opposite sides of that line that runs through the double bond, so that's the E isomer. So that's E pent 3-ene 2-one would be the full name for that compound. And this one, this time we've got 2 ketone groups. Okay, so they both fulfill this description that the C double bond O has carbons on both sides. So 2 ketone groups is not just an one, it's a dione. So you're very used to now these dienes and diols and now diones. So if we count the number of carbons, we've got 1, 2, 3, 4, 5, 6 altogether. So it's hex. It's saturated, no carbon-carbon double bonds. So it's hexan. And then we're going to need numbers to show where the ketone groups are. So we'll start numbering at this end to keep the numbers smaller. So we've got a ketone group at 2 and also at 3, because it's 1, 2, 3, 4, 5, 6. So it's hexan 2, 3 dione. So question 14 gives us our first examples of this really important type of reaction, which is oxidation of an alcohol. So you need immediately to learn to recognize the oxidizing agent, which is aqueous acidic potassium dichromate. So when you're learning this, make sure you learn that whole package. It's not just potassium dichromate. Without the water, without the acid, it won't work. So it's got to learn the whole package, aqueous acidic potassium dichromate. The formula for that is K2Cr2O7, which you may sometimes see, but mainly you're going to work with the name. And that's used for oxidizing primary alcohols to make aldehydes or carboxylic acids, and we'll get more into that later. Secondary alcohols to make ketones. It cannot oxidize tertiary alcohols. So you need to learn that story because that's quite a complicated sort of set of things that you have to take on board. But these questions will help you practice it, but make sure you go through it thoroughly in the notes first so that you've understood the different patterns of reaction with the different classes of alcohol. So, the other thing that you need to know about it is that when you write equations for oxidation of alcohols, if you try to balance it with this actual formula, with the potassium dichromate, it gets hideously complicated. Because actually the acid is also involved in the reaction, so there's H plus involved in the reaction. And just to give you an idea of why it gets very complicated, for each dichromate ion that reacts, 14 H plus ions have to react. So you can see that balancing the equation is going to get really messy and complicated. So organic chemists can't be bothered with that. And so they use this wonderful cheat, which is that they use this to represent the oxidizing agent. So this is the oxidizing agent because it makes the alcohol become oxidized, but in the equation you just represent it as an oxygen atom with a square bracket around it. And that makes life enormously easier because then it makes balancing the equation very easy, and everybody understands that that's just shorthand for whatever oxidizing agent you happen to be using, but the only one that we're going to learn is this one. Okay, so let's see how that works. So butan-2-ol is this. There's the butan, chain of 4, and there's the OH group on carbon 2. So that's a secondary alcohol. And when secondary alcohols are oxidized, they make ketones. And you can see how that's going to work. But what happens in the oxidation is that the oxidizing agent takes away the hydrogen from the OH group, and it also takes away a hydrogen from this carbon that it's attached to. So it takes 2 hydrogens away, one from the OH group, one from the carbon that it's attached to, and those 2 hydrogens, in your equation at least, combine with this O in the oxidizing agent formula to make a water molecule. So we have that plus magic oxygen. I tend to call it magic oxygen. Don't call it that in an exam, but it's just a convenient way of remembering that symbol as a magic oxygen. So you've got to take away the hydrogen from here, you've got to take away the hydrogen from there, and in its place you get this double bond. So in other words, you get a ketone group like that. So we're going to get butanone. And as I say, to balance up that equation, those 2 hydrogens that you've removed to make it possible to make that double bond, plus that magic oxygen, give you water as your other product. Okay, so then 4-methylheptan-1-ol, 1, 2, 3, 4, 5, 6, 7 is your heptan bit, saturated chain of 7. Carbon 1 has an OH group on board, so this will be carbon 1. So carbon 2, 3, 4 has a methyl group. Okay, so that's 4-methylheptan-1-ol. So you can see this time it's a primary alcohol. And when primary alcohols are oxidized, it's more complicated because there's more than one possible outcome. With the secondary one, ketone is the only possibility. But with a primary one, it depends how long you oxidize it for. If you just do it for a short time, you oxidize it to an aldehyde. Okay, secondary goes to ketone, primary goes to aldehyde. It's essentially the same reaction, but because it's at the end of the chain, you get an aldehyde rather than a ketone. If you oxidize for longer, something different happens, which we'll get onto in a bit. But in this question, it's specifying brief oxidation. So it's just going to do exactly the same kind of thing that butan-2-ol did here. So there's the oxidizing agent. It's going to take away a hydrogen from here and a hydrogen from the attached carbon, and we're going to get a double bond there. So we'll get this with now double bond O on the end and H2O. Okay, so this time we've turned a primary alcohol into an aldehyde. So secondary alcohol goes to ketone, primary alcohol goes to aldehyde. And you can see it's the same pattern of reaction. It's just that because the carbonyl group's at the end of the chain, it's a different type of functional group. So then we have to think about this compound, 2-methyl pentan-2-ol. So pentan, chain of 5, and carbon 2 has the OH, but also a methyl group. So it's that. And that, you can see, is a tertiary alcohol, because the carbon with the OH has 3 other carbons attached. And tertiary alcohols, if you expose them to an oxidizing agent like this, they just take no notice. So there will be no reaction with aqueous acidic potassium dichromate because it's a tertiary alcohol. So tertiary alcohols don't react. Why not? Well, you can see, because remember the pattern is that the oxidizing agent has to come along and take a hydrogen away from the OH group and a hydrogen away from the attached carbon so that you can put a double bond there. And you can see the problem that the attached carbon doesn't have any hydrogens. It's got 3 other carbons attached, so there's no room for any hydrogens. So it can't form that that necessary water molecule because there just isn't a hydrogen there to take away. So tertiary alcohols, no reaction. That can be quite useful, not just as a these reactions are useful not just as a way of making things, but also you can use them to distinguish tertiary alcohols from primary and secondary ones, because aqueous acidic potassium dichromate is orange. It's bright orange colour, and when it reacts, the dichromate changes into Cr3+, which is green. So what happens when you do the reaction is that if the dichromate succeeds in oxidizing something, it itself becomes reduced to Cr3+, and so the colour changes from orange to green. So with a tertiary alcohol, there was no reaction, so the dichromate will stay orange when you heat it up. But with a primary or secondary one, if you heat it with the aqueous acidic potassium dichromate, it changes from orange to green. So that's an important colour change that you need to learn. So remember, the dichromate ion is orange, gets reduced to Cr3+, which is green. So orange to green is your evidence that the dichromate got reduced, and therefore it must have oxidized something. Could be primary alcohol, could be secondary alcohol, but not tertiary. So that's quite a useful test. So question 15 is now saying, okay, what we talked about so far is what happens if you oxidize briefly with aqueous acidic potassium dichromate. But what if you allow the oxidation to carry on for a longer time? What if you have excess of the dichromate and you allow it to react for as long as it takes in order to go further if it can? What's the outcome for each of those compounds? So butan-2-ol we started with, and we've already said this is the first stage of reaction. So we had a secondary alcohol, butan-2-ol, and it was oxidized to a ketone, butanone. So the answer then is that if you keep on exposing it to the oxidizing agent for longer, it makes no difference. Okay, so that one has no further reaction because you just can't do anything more to a ketone. So that's the end of the line as far as oxidation is concerned. So for secondary alcohols it's easy. They just don't change anymore once they've been oxidized to the ketone stage. Now for this one, which is the primary alcohol, we saw that the first stage of oxidation is that the alcohol is oxidized to an aldehyde, and so we'd get 4-methylheptanal, which is that product there. And again the question is, well, what difference does it make if we then expose it to the oxidizing agent for longer? And the answer is that this time it does make a difference, because aldehydes themselves can be oxidized in a way that ketones cannot. And what happens to them is something quite simple, and it produces a functional group which you've met before, in fact, when we learnt about acids and bases in the first term. And what happens is that this is converted to a carboxylic acid group. So ketone group is still, sorry, the carbonyl group is still there, it's not a ketone. So we've got all of that is still there, and all that happens is instead of just having a hydrogen there, so instead of just being CHO at the end of the chain, that becomes an OH. Okay, so we go from primary alcohol to aldehyde to carboxylic acid. Okay, so what we get there is called 4-methylheptanoic acid. So that's the complicated story. You've got to remember that primary alcohols are the complicated ones, and it means that you've got to be careful and make sure you understand the conditions of oxidation. So brief oxidation gives that, prolonged oxidation gives the carboxylic acid. We'll talk more in later questions about how experimentally you actually make sure that it stops at this stage if that's what you want, or carries through to that stage if that's what you want. So the overall equation for that oxidation from there to there, primary alcohol to carboxylic acid, is going to go like this. So if we put down our primary alcohol like that, it's going to have to react this time with 2 moles of oxidizing agent. Okay, because you need a mole of oxidizing agent for each of these steps, so 2 moles altogether. So that gives you your carboxylic acid product, which is this. And just the 1 water, because that first stage of oxidation, you saw that we took 2 hydrogens away. Right, took a hydrogen off here and a hydrogen off there in order to make it possible to make the double bond there, and those 2 hydrogens combined with the magic oxygen from representing the oxidizing agent to make water. But in this second stage of oxidation, you can see that all you're doing is adding in an oxygen. In effect, it just tucks an oxygen in between the carbon and the hydrogen there. So there's no loss of hydrogen, no more waters are formed. So you've got to remember that, because you don't want to have to figure it out like that on the day, that you need 2 moles of oxidizing agent to go through to the carboxylic acid, but you only get 1 mole of water formed as a product. So then finally we had our tertiary alcohol, 2-methylpentantool, and we said that with brief oxidation with the aqueous acidic potassium dichromate, actually you get no oxidation, there is no reaction. And if you expose it to the oxidizing agent for longer, there is still no reaction. You just can't do anything with that tertiary alcohol because there is no hydrogen here to eliminate, to allow that first stage of oxidation. So there's still no reaction. End of story.